right, good afternoon. So today we're going to look at section 29C, which is expectation or expected outcomes. So let's just consider the following question just to get started. Let's say you roll a die 120 times. On how many occasions would you expect the result to be a 6? Now I'm sure a few of you are shouting out that we should just multiply by a sixth or divide by 6. That's logical. So we're going to take 1/6 times 120, and we would expect that 20 times we would roll a 6. Likewise, we would expect 20 times to roll a 1, a 2, a 3, a 4, and a 5, etc. In general, if there are n members of a sample, and the probability of an event occurring is p for each member, then the expectation of the occurrence of that event is just n times p. In other words, if you have n possible outcomes and each of them has an equal probability of occurring, which we're calling p, then the expectation is just n times p. That's how many times you would expect each individual event to occur. So let's look at a basic example. Let's say the probability of it snowing in Indiana on any given day in February is 0.37. How many days would you expect it to snow in the month of February? Well, we're just going to take n times p. Well, in this case, and you've done probably this in the past, but in this case, n is just the number of days in February. Although this is leap year, let's say it's not, the number of days generally in February is 28, and the probability of it snowing is 0.37, so the expectation is 10.36 if you multiply those numbers together. Now, that doesn't really answer the question. How many days would you expect it to snow in the month of February? Well, if it's 10.36, we would expect it to snow, or round appropriately, on 10 of those 28 days. Okay? You've already been doing this in the past. This should be nothing new or surprising to you. But let's now look at a slightly more complicated scenario. So, in a particular gambling game that costs $3 to play, one card is drawn from a standard deck, and the returns to the player are given in the table below. So, you pay $3, you play this game, there's a deck of cards, you just randomly draw one card. If you happen to draw an ace, you win $10. If you happen to draw a face card, that's a jack, a queen, or a king, you win $5. If you happen to draw any numbered card, 2 through 10, you win nothing. So you lose your money. So the first question asks, what are your chances of playing one game and winning, first off, $10? Well, in order to win $10, you got to draw an ace. So, how many aces are there? Well, if you know a standard poker deck, there's 4 aces out of 52 cards. So the chances in one game of winning $10 is 4 out of 52, which reduces to 1 out of 13. Well, what's the chance in one game of winning $5? Well, to win $5, you got to have a face card. You can think of this a couple different ways. There's 3 types of face cards, Jack, Queen, and King, of which there are 4 each. So that would be 12 face cards out of 52, which reduces to 3 out of 13. The other way you could have thought of that is that 3 out of every 13 cards are face cards, because there's 13 cards each suit, and 3 of them are face cards. Likewise, if we go back here to the 1 out of 13, for the aces, there's 1 ace for every 13 cards in each suit. Now, last question, what's the probability of winning $0 on any game? Well, that's just the rest of the cards. So you could count them up and find that from 2 to 10, there are actually, let's see, do the math, 52 minus 16, that would be 36 cards. So it would be 36 out of 52. Which reduces to 9 out of 13. Or you could have just used the fact that there are 9 face cards out of each 13 cards in a suit, or you could have subtracted the 1/13 and the 3/13, leaving you with 9/13. Okay. Well, that's something you've done in the past. That also should be fairly familiar to you. Now we get into something a little different. So now we're asking the question, what is your expected return from drawing each of the following cards? So how much are you expecting to make in one turn from drawing an ace? Well, what you have to do to calculate that is take the probability of drawing an ace, which we already calculated as 1 out of 13, and you have to times that by the winnings. In this case, $10. If you multiply that out, accounting for money, round to 2 decimal places, you get 77 cents. Now, what does that mean? That means that on any one game you play of this made-up game, you can expect to win on average 77 cents from drawing an ace per game. Now, will you ever win exactly 77 cents? No, that's not possible. You're either going to win 10, or you're going to win 5, or you're going to win 0. But on average, over the long haul, you can expect to win 77 cents off of the aces per game. What we're doing is we're really thinking more from the perspective not of the player as much as from the perspective of the casino, because they have to consider this when they're devising a game. Well, how much would we expect each person to win off of a face card? Well, we got to take the probability for a face card, which is 3 out of 13, and multiply that by the winnings, which is $5 for a face card. That gives us a grand total of $1.15. So each time you play the game, you expect on average to win $1.15 off of face cards. How much do you expect to win from drawing a number card? Well, it's 9 out of 13 is the probability there, but we know that the winnings is nothing, is 0. So multiply anything by 0, the expected winnings from the face card, or the number cards, is 0. All right, so overall, question number 3 wants to know, what is your expected result at the end of one game? Well, at the end of one game, we would expect on average to make 77 cents off an ace, $1.15 off of a face card, and 0 from each number card. So if you add those together, you will get a grand total of $1.92, which means you expected on each game to return back to you an average winning of $1.92. Well, what does that mean? What's your expected result? You paid $3 at the beginning of the game. If you paid $3 and on average you expect to get $1.92 back, then that means your expected result each time you play the game is to lose $1.08. That's what the casino's interested in. That means the casino's expecting each time to make $1.08 off of each person that plays that game. They've got to keep it so that it's profitable to them, but not too profitable so that it scares people off and they never want to play the game. Okay, so you're expecting overall to lose $1.08 each time you play the game. Next question, last question here. What's your expected result if you play 50 games? Well, if you lose $1.08 each time you play, and you play 50 times, well, that's just 50 times $1.08, which means overall you expect to lose $54. If you play the game 50 times, you can expect to go home having lost a net total of $54. All right. Let's look at this from a more mathematical perspective. The expectation or expected outcome, which we call E of x of a random variable x, is defined as the following. We have E of x equals, notice this is the sum of each probability, P sub I, times each outcome, X sub I. Where X sub I represents particular outcomes, P sub I represents the probability of X sub I occurring, and X is the random variable we are concerned about. In many cases, it's the return. Now, what this means is we're going to take each probability, so probability of event number 1 times the outcome for event 1 plus the probability of event 2 times the outcome for event 2. All the way up to the probability of event n times the outcome of event n. In other words, we're going to do what we just did on the previous one. We're going to take each individual outcome's probability times whatever it produces, a lot of times that's the return, add each of those individual probabilities and outcomes together to give us an overall expected outcome. So, let's look at this scenario. Let's say a die has 3 blue, 2 green, and 1 yellow face. When the die is rolled, a blue result wins $2, a green result $3, and a yellow result $9. How much would a person expect to win playing this game once? Okay. Well, the expected outcome, E of x, is just the probability of each outcome times the amount you gain from that outcome. So if we wanted to roll a blue, there are 3 blue faces, that's 3 out of 6, or a probability of 1/2, times the winnings. Blue wins you $2, so we're going to multiply that by 2. Plus, the next outcome, we could potentially roll green, that's 2 out of 6 faces, or 1/3, times the winnings for green, which is $3. Plus, the last outcome is yellow, which is 1 out of 6 faces, times the winnings for yellow, which is $9. If you add all of those together, you get $3.50. That's how much a person would expect to win playing this game one time. So, if the organizer of the game, could be the casino, could be whatever, the organizer of the game wants to make an average of $1 per game, how much should he or she charge to play the game? Well, if we're expecting on average each person to profit, well not profit, but to earn $3.50 each time they play it, and we want to overall keep a buck for ourselves, then logically that means we need to charge $4.50 per game. So if we charge $4.50 and they make back $3.50 every time they play the game, then we, on average, earn $1 per game. These are the types of thought process casinos have to go through when they're deciding how much winnings per game and how much they should charge per game. Okay? All right, one more scenario. A game is played in which a pair of dice is rolled. If doubles are rolled, then $8 is won. If the difference between the numbers on the dice is 1, then $3 is won. If the difference between the number on the dice is greater than 1, then $2 is lost. How much would you expect to win when playing the game once? How about when playing the game 15 times? All right, I'm going to have you guys try this on your own. Once you've tried it on your own, confer with someone else. My only suggestion is right here when it says $2 is lost, when you plug that in, a loss is represented by a negative. So you want to make that a -2 when you plug it in. So each time, take the probability of that outcome times the gain or loss for that outcome, plus the probability of the next outcome times its gain or loss, so forth and so on, and get a total. Do it first just to find the the expected outcome for playing the game once, and then the expected outcome for playing the game 15 times. Go ahead and do that right now on your own. Try it for a few minutes, and then check your results with one another.